Okay, today is the 31st of October 2024. Happy Deepavali. And we are now at Z Transform, the second lecture. It should be 2 hours long. And once we are finished with this, we are done with Z Transform. So in today's lecture, I'm going through um, mostly chapter 5.4. And in chapter 5.4, we'll go through very quickly. And the most important part of chapter 5.4 is the last three slides. So it's from page 27, 28, and 29. So once you can do these last three slides fluidly, you can do the lab, of course, and then you can also do the exams. Now, you will realize that in the exams, we will not be able to give you very complicated functions because it is impossible to partial fraction expansion for 3 or 4 degrees. So we are going to restrict to two or third order polynomials for poles and zeros. Okay, we'll begin with this diagram. And we'll begin with the difference equation first. And then once we understand what is a difference equation, then we will start. Okay, so let's begin. Now, let's do the simplest difference equation that we can have. Y of n is equals to 2xn. And if this is the system LTI, and this is y of n, and this is x of n, then guys, please participate. All right. What would what would what would that block LTI looks like? Okay. I mean, this is trivial, right? It just says my output is 2 times my input. So you should be drawing something like this too. And this is y of n. So if I have given you an equation, you know how to draw the block diagram, the realization of it. And then now if I ask you plus 1xn minus 1, now what does 1n my xn minus 1 mean? It basically means that I'm going to add to my output a delayed version of my input. So I will introduce a delayed version. So this is the delay operator z minus 1. And here is xn minus 1. So how do you do it in a real circuit? Basically, it is a memory. You say that I use a memory or a lookup table to delay my sequence. Okay? And then now I have to sum. So this is addition, addition, and now x of n, y of n is equals to 2x of n, and then here the constant 1. So if I really need to, I should write a constant 1 here. 1. This is a triangle as a multiplier. And then let me draw it nicely for you. This is 1. So therefore, this is plus 1 x of n minus 1. So this is all very easy. And of course, if we keep on doing this, z minus 1, this will be xn minus 2. And now let's plus 4xn minus 2. Of course, you can multiply by any number, okay, any real number. And this is plus 4xn minus 2. Okay, now in the left, this is called the difference equation. And on the right hand side, this is called the block diagram realization of the difference equation. And there are many, many block diagram, and we're only going to use the simplest block diagram called direct form 1. Okay, so let me ask you now, what is the impulse response of the system. So that's we are going to ask you all the same question, guys. So the easiest question that we'll ask you is what is the impulse response? Anyone can tell me, please? What should you do? I mean, when you're faced with this question, and then you're saying that I have this what do you call that? This equation, I have this block diagram. How do I find the impulse response? Anybody? Please. There's only 13 of you, 12 of you. Z transform. Yeah, but that's the most difficult approach, right? That's the most difficult approach. Let's do it by brute force, all right? So I'm going to draw for you a brute force approach, and let's try 214. All right, let's try y of n equals to 2 of xn plus 1 x of n minus 1 plus 4 x n minus 2. Please, whether it's plus or negative is totally up to you. Okay, so I'm going to show you by brute force. Let's say this is n is minus 1. Let's say this is x of n. This is x of n minus 1. This is x of n minus 2. And this is y of n. Now we're going to ask you this. The system is relaxed, guys. What does the system is relaxed means? Please answer the question. The system is relaxed. So system is relaxed. Yes, all the memory is 0. Where are the memory? Here. Here's the memory. Xn minus 1 is a memory. Xn minus 2 is a memory. Xn is 0. Okay, there's nothing. No one is feeding anything, and all the variables within the system is 0. So Xn minus 1 is 0, Xn minus 2 is 0. And also, so let's put all the 0 here. And Xn is 0 because I'm going to send an impulse, right? So I want to find impulse response. If I want to find impulse response, what does Xn look like? If this is 0, 1, 2, 3, 4, and this is n. What does Xn look like, guys? Yes? What does Xn look like? If I want to send an impulse, if I want to get an impulse response, the question is find the impulse response. So Xn must be equals to delta n. What does delta n looks like? It spikes. Yes, it's not a spike actually. You must be very careful. It is 1. Okay? And it is not a spike. Huh? In a continuous time, it's a spike to infinity. But in discrete time, it is 1. And then you're right, the rest are all 0. No, no, no. Julian, we are finding the impulse response. So I'm telling you what xn look like first. Okay? And xn looks like impulse and 0, 0, 0, 0. The impulse is value 1. Okay, so at time n equals to 0, what do I get? What is xn, guys? So you look at this figure. Oh, of course, xn is 1. What is xn minus 1? What is the value of xn minus 1? Let's look at the figure. Xn was originally here. As time progressed, it will move down. Pa! So xn minus 1 came from xn. And xn minus 2 came from xn minus 1. So, and so if I call this A, this is, if I call this B, if I call this C, do you get it, guys? So far, everyone happy? 0A comes to here, 0B comes to here, 0C goes to nowhere. Why? Because you look at the figure again. This guy goes to nobody because nobody's interested in him anymore. He's just dropped. Ish. All right. Now let's add yn is equals to 2xn. So it's 2 times this guy, 2xn plus 1 times this guy plus 4 times this guy. So the answer is 2 times 0, 1 times 0, 4 times 0. Answer is 0. Okay? Now, what about here? 2 times 1 plus 1 times 0, 4 times 0. So it's 2. So now, let's see. Time 1. What else am I going to draw, guys? What is the most interesting thing that's going to happen now? The new xn is what? The new xn is 0 at time 1. At time 1, n equals to 1. Input xn is 0. So I'm going to circle this guy. This orange guy is 0. Okay, let's call him 0D. So he is 0D. This 0 is popped into here, xn, push in. What happened to 1, guys? Just look at the figure again. 1, which was original here, will be pushed into xn minus 1. So this is 1. And now we're going to push 0a here. And now the output is what, guys? 1 times 1, because the rest is 2 times 0, 4 times 0. So this is 1. So far, okay, guys? Brute force, huh? So actually, if you write a code to do this, it will be like 3 lines of code. Okay? And 2. And therefore now, we're going to push in 2, which is, let's draw this, use this guy again. And this guy, let's call him 0e. 0e. So 0d is being pushed into here. Oops, I used the wrong color. And then he's being pushed into here. And now output is 4. Right? So what's going to happen one more time, guys? If I'm going to ask you to find one more row. So time 3. And you'll notice, of course, is that if I use this guy, it will be 0f. And 0f is going to be pushed here into my input, xn. And now, of course, the rest of the memory is going to be pushed into the next delayed version. So xn will be pushed to xn minus 1, 0e, 0d. And now, tell me, guys, what is the output? Please? Very good. 0. And you realize that now all the inputs will always be 0. Therefore, the 0 will continue to infinity. So this is a very interesting, it's called finite impulse response. Why finite? Look, the impulse response is only n 0, 1, 2, 3, 4. And the number is only interesting 214. 2 at time 0, 1 at time 1, and 4 at time 2. And then the rest is all 0. 2, 1, 4. And this is h of n by brute force. Clear? Okay. So now, I mean, now you really realize what does a difference equation do, the simplest difference equation, going into a block diagram. And if you are VLSI guys and you work for, uh, NVIDIA, you'll be programming these like a billion of them, right? Memories. And you are shuffling all these vectors and elements into multipliers and summing. That's all you're doing, really. or this GPU. All right. Now, there's only about 13 of you. Can I ask you all to turn on your camera, please? Actually, normally I don't, but yeah, I think it's. May I, please? All right, great. What are you all doing here on the Deepavali? Yeah, I wish I'm somewhere else anyway. But okay, wait, okay. So now you're the rest. Okay, I got two guys. Come, I'm waiting for the rest. And all right, and I'm going to show you uh, some other things as well. Now, I hope you all have been watching this uh, this YouTube videos, right? Signal systems. Yes? Anybody? Okay. So we are now at Z transform. So if you are a little bit lost today, you just go through chapter 5.4 and 5.5. This is where I am today. But I'm going at different speed. Okay? So if you look at this and you don't understand, actually, in the lectures, I'm going at a very slow and very detailed speed. In here, right, I'm actually going to jump very, very fast. Okay, you might not feel it, but it is much faster normally. All right. So I have done two equations, guys. Sorry, I've done a difference equation and a block diagram, and I've done a brute force approach. So now let's make our equation more complex, our difference equation. Okay. All right. Let's try. So I'm going to use our lecture, our this lecture. I'm going to use this equation. And then now we are going to study the difference between this equation. Actually, this equation looks very close to our previous equation. What's the difference? Yn is equals to xn plus xn minus 1. Now this is the interesting part. Plus 1/3 yn minus 1. Okay, so let's see this equation and we'll do it together. All right. Now I got three guys with the camera on. What about the rest of y'all? Please. Okay. Okay, let's try. Oops. I just lost my pen. Oh, zero battery. So I have no battery now. I'm charging my pencil. Yeah, let's try the rest of you guys. So I have now one, two, three, four. Actually, may I? I mean, since we're in the holiday mood, could I just chat with you? How is the how is the school asking you to come back for tutorial doing for your studying? Is it better deal or not better deal? You're talking to a wall, guys. Oh boy, not good. Yeah, but I know that those guys who live far away would find hopeless. But honestly, it's. Oh, I'm asking, getting you guys to come for tutorials, is it a good deal or not very good? Okay, so, but not very good for everyone, especially students live far away. Yeah, that's true. I understand. But actually having you guys come for tutorial class, right, is highly motivating for at least for me, and also that you guys should get to know each other across the years, right? Okay. All right. Let's do some signal processing now. Yn is equals to xn plus xn minus 1 plus 1/3 yn minus 1. Now, the interesting and the most exciting thing that happens is the additional adding what? Pass output to the system. And how would we draw this, guys? Let's draw it again. So xn, and now I'm concentrating on this gain. This gain is 1, and then this is my output, y of n. So the equation, of course, is simply 1 times xn, because there's only one line passing through one gain. All right, now I have the second line, guys, passing through a delay, passing through a gain of 1 again. This is the adder, and now this is xn minus, oops. Now if I make a mistake, guys, please shout at me. And this is 1 again. Okay, so if I color code this so that you know that this is the green one and this is the blue one. Okay, so you say, oh, this is 1 times xn. This is 1 green times xn minus 1. So therefore, plus, this is the green. 1 green times the xn minus 1. Now, so how I'm going to draw and sketch yn minus 1 times 1/3, guys? Same. And, and then it is the output delay by 1. And this is yn minus 1. And he's going to multiply by, let's say, this guy. And this guy is 1/3 plus. Okay? So this sign will confuse a lot of you guys. Okay? Now the equation say plus 1/3. So it's there, sitting there, plus 1/3. So it's plus 1/3 yn minus 1. And then that's it. That's the equation we have, and we now know how to draw the block diagram. So there's 2 marks in the exams, guys. If we ever ask you to draw DF1, this is called the direct form 1, and it comes from the difference equation directly. So now let's jump, okay? What is HZ? Give me some names, guys. HZ has a name. Yes, transfer function. Very good. And the definition of a transfer function is equals to, anybody? HZ is equals to who over who? Who is transferring? Yes. It is always the output over the input. And we always call the input X and we call the output Y. So we need Y and Z. All right. Let's perform Z transform on this equation on the top. Okay. So this is the table that you need. If my time is X of n, Z transform, what is the symbol that I'll write here, guys? I repeat. This is xn. On the symbol on the right is xc. That's all. And if this is yn, this is yz. And if this is xn minus 1, this is, yes, this is z minus 1, the delayed version of x of z. And therefore, x of n minus 2, z minus 2, x of z. So with that, we can now do the top equation. Okay, so what do I do? Ah, how do I cut this? Never mind. I'll just I'll just rewrite this equation on the top one. 1xn, 1xn minus 1, 1/3 y minus 1. Okay, come. So yn is equals to 1xn plus 1xn minus 1 plus 1/3 yn n minus 1. And now the Z transform. Now, now this is going to confuse some people. This plus 1/3, right, is going to change sign because I'm going to move this guy to the left hand side. And that is why students are confused and they draw for me the wrong sign because sometimes I will give them in this form and then when they are drawing this guy, they put a minus here. Okay? So that's the trick. So just by brute force you should be doing this. And then when you move the right hand side plus 1/3, you become minus 1/3 Z minus 1. Okay, and we have the transfer function finished, right? Another 2 marks in the lab. And the next question, of course, is so where are we now, guys? So look at that figure. We have we have the difference equation, we have the block diagram. So either I give you the block diagram, you find the difference equation, or you are given the difference equation and you generate the block diagram. Now, the transfer function, you just do the Z transform. So, but my equation is in positive powers of Z. Z plus 1, Z minus 1/3. So let's convert. So we never really like the negative powers of Z. It's not intuitive. So we multiply top and bottom by Z. Z plus 1, Z minus 1/3. So once we have this, then what is the pole zero? Okay, what's the pole zero diagram? First and foremost, guys, one. What is Z? Anyone? Complex. Okay, it's not, yeah. So Z is the complex number, the set of all complex number. So I say Z. What I mean is you can use any Z in the world that you like. Okay? Now, if I say that you can use any Z in the world that you like, what you should do for me is this. This is the real Z, and this is the imaginary Z. And the values now, this guy is the origin, this guy is 1, this guy is 2, this guy is 3, this guy is minus 1, this guy is minus 2. And as we go up, this is J, this is 2J, J, minus 2J. And then you say that you can choose any Z on this plane. So we call this the complex plane, the set of all complex numbers. Now, just like before, in the Laplace, we also have the complex plane. But now, I'm going to ask you to draw a circle. I will insist that you draw the unit circle for me. What is a unit circle? It is this circle of radius 1. See, you can see that go up is 1j, go down is minus 1j, go right is 1, go left is minus 1. So the length of this circle from the origin is always 1. And it's spinning. Guys, how is it spinning? When I ask you, I have the complex number, the unit circle. What is my omega, my theta? So so my z is now 1 ej omega. What is my omega? 1. What is 1? 1 is the unit length. Theta is now omega. So actually, I should draw for you. This is omega. And now omega, this point is 1 ej omega, whatever omega is. And what can my omega be, guys? What is the range of omega that I can use for this unit circle? Anybody? 0 to 2 pi. Excellent. Okay, so omega can be 0 to 2 pi. Okay, and it's 0 to 2 pi because I can start, if my omega is 0, then I'm along this blue line. As I increase my omega, I'm moving anti-clockwise. And if I reach 90 degrees, I'm pointing upwards. And if I reach 180 degrees pi, I reach point here. If I reach 1.5 pi, I reach here. If I reach 2 pi, I point back at 0 angle. So it is only 0 to 2 pi. Okay, now, so therefore, my omega is from 0 to 2 pi. All right. Okay, let's come back to this equation. Now the question is, I want to draw the pole and zero diagram of this equation. So h of z equals to z plus 1, z minus 1 third. Now, guys, I can substitute any z, right? Let's substitute the simplest z. What is the simplest z that I can substitute, guys? Please. What's the simplest z? The no-brainer z. Come on, guys. No, the simplest z is not minus 1 and 1 third. Well, I can. Minus 1 will give you 0 on top. Fine. So when you do minus 1, excellent. 0 is the one, the number I want. What is h? Z equals to 0, the simplest number. Then you just say, hey, isn't it just simply 1 divided by minus 1 third equals to minus 3, right? So, what is z at equals to 0? Where? Where the word is z equals to 0? It's here, this point, right at the middle, the origin. So at this point, minus 3 comes out. Yeah? Actually, minus 3 will go down. You have to think where minus 3 is going. And it's a real number. Okay, and you plug any complex number in. I mean, you can plug in j, right? Then it's 1 plus j divided by j minus 1 third. Then you get some complex number here. And you can plug any values here. And then you finally say, oh, I can shade this h of z. Okay, that's what h of z is. H of z is nothing but a surface on the z plane with complex numbers. Yeah? All right. Now, so now, of course, comes to the exam question. Where are the poles and zero? Pole, let's do the zero first, which is more intuitive to me at least. Zero means what? H of z equals to 0. So when h of z equals to 0, what is z? So this is the what value of z such that the output is 0? Guys, minus 1. Right, when you put minus 1 here is minus 1 plus 1. So on top is 0. Whatever bottom is, we don't care. So when z equals to minus 1, where's z equals to minus 1? This is real of z. Minus 1 is here. We're going to draw a circle here. This circle is saying z equals to minus 1 is a 0. A 0 of h of z. If you really want to be pedantic, it's not a 0, right? It is just at this point, when we substitute z equals to minus 1, h of z becomes 0. Pole, guys, 1 third, right? Pole, when z is 1 third, the denominator becomes 0, therefore it becomes infinity. So where's 1 third, guys? 1 third is about here. When z is equals to 1 third, h of z equals to infinity. Therefore, z equals to 1 third is a pole. So that's what we are saying. That's all. So we now know how to draw the pole and zero diagram from this guy. Clear? All right. Now, I want to switch gear a bit. In MATLAB, the numerator is often called b. and the denominator is often called A. And the coefficients are 1 and 1. Can you see the 1 here and the 1 here? So we put 1, comma 1. Two elements. Here, 1 and minus 1 third. 1 and minus 1 third. So with these two vectors, I have represented HZ. Represents what? The polynomials in Z minus 1. Huh? Okay, come, let's. Can you see my screen still, guys? I know it's small. Close or clear or. B is equals to 1, 1. Can I make this bigger? I can't. A is equals to 1 minus 1 third. Z plane. B comma A. Can you see the 0 at minus 1 and the pole at 1 third? And they draw the unit circle and he called this line the real part. This is 1, 0 and minus 1. Along the vertical, he called it the imaginary part. Here is minus j, 0j, 1j. And this is a unit circle. Finish. So actually, once you can identify the h of z in what? H of z in which form, guys? In the negative powers of z, all you need to draw the pole and 0 is to call one function. Just call z plane b comma a. Finish. Okay, so if you are doing your lab, you're just calling MATLAB to do all this. Of course, if you're in the exams, you can't. You have to do factorization and push whatever all this. But in MATLAB, if you have MATLAB sitting there, it's one line of code. Okay. All right. Now, what else? Any questions, guys? Okay. No, I'm going to show you this. Help filter. So you realize that MATLAB uses B and A as the coefficients of the difference equation. There. All right. So you must be very careful. Huh? So I'm going to write the difference equation for you now. Okay. So this highlighted blue, I'm going to repeat here so that you know what I'm talking about. What was our equation? Y n equals to xn plus xn minus 1 plus 1 third yn minus 1. Now, where's the B's and the A, guy? Where's the B and the A? So you have to go back and then you realize who's the B? The B's are multiplying the X's. Okay, let's go there. So this is B1. This is B2. Unfortunately, MATLAB uses index 1. And that's going to cause you a lot of pain, okay, later on. But if you don't care, I mean, as in, we have to live with it, huh? So can you see? B1, the first element is multiplying by xn. B2 is multiplying by xn minus 1. Okay, and we are adding. And then now look, he's going to say minus A2. Oh my God. That's why the notations is very, very confusing when you are reading MATLAB and your code. So, so, so what's happening? I'm going to write here. This guy is supposed to be minus A who? 2. Where is A1? A1 is sitting here. Okay, let's write some numbers. B1 is 1, B2 is 1. A2 is my so I'm always confused here. Is A2 minus 1/3 or A2 plus 1/3? So let's go back up again. So you realize, okay, A2 is minus 1/3. So that's right, A, B again. So B is easy. 1, 1. A, 1, 1 what? Plus 1/3 or minus 1/3, guys? Minus 1/3. Because on the right hand side, we have to shift it to the left hand side and it becomes minus 1/3. Okay? And now let's be very clear of this notation. This is A1. This is A2. This is B1. This is B2. Sorry. I should use capital. Okay? All right. So now, all right, just get these facts right. And then you can be playing with MATLAB easily. Okay? Once your one of the sign is wrong, your whole answer is finished. Huh? There's nothing to we're not even going to look at your answer anymore because there's nothing to look at. Does z plane function also work for positive powers of z? No, you see, guys, you must be very careful. The whole notation is in negative powers of z. Okay? Help z plane. The z plane, the b's and a's are the transfer functions. Yeah, so you have to go and read how are they interpreted, and you realize that they are always in the negative powers of z. All right, that's why there's a very subtle. I mean, you get everything wrong if you use positive powers of z. Sometimes you don't, but sometimes most of the time you will get it wrong. All right, okay, so I'm done now. Mm. Now, guys, I have shown you the impulse response, right? Where's my impulse response? Oh, so I've done the block diagram, I've done the difference equation, I've done HZ, I've done poles and zero. Okay, I forgot to draw the hairy thing. The hairy thing here that's sticking out is showing you the region of convergence. So back to this question here. The pole is sitting at 1/3. What you need to do is to draw a circle of 1/3, and then now you're going to draw the hair sticking out from this, and this shaded region is called the region of convergence of this h of z. And if the region of convergence touches the unit circle, then we tell you that the system is stable. Why? Go and look at the lecture notes. Okay, so that means whenever you put any values of z here, this h of z, okay, no problem, you get the correct h of z. Now if you try to put any values inside 1/3, any of these, right? Maybe 1/4, okay, plus 1/4 j, whatever value, or in fact z equals to 0, then actually, then you say, hey, when z equals to 0, sorry, what did I do? H of z equals to 0. Then you say, isn't it nothing but 1 over minus 1/3, right? And then you realize, hey, it's equals to what? Minus 3. you realize that minus 3, even though you can do this value, is totally wrong. Nothing to do with HZ at all. Because this closed form solution only is valid outside this circle of 1/3. Okay, that's what it means. Every time I give you a closed form expression, you must know the region of convergence. What value of Z will be correct representing this? You put it out of the region of convergence, although you can get a number, totally wrong. Okay? So please remember that. So that was a trick question just now when I asked you substitute Z equals to 0. Then you all happily substitute Z equals to 0, get minus 1/3, and this is rubbish. All right? Okay. Now, the filter. So impulse response. Now, guys, if you are in the lab, please don't do the brute force method that we did. Okay? In the exams, too bad. You have to draw this table and my brute force you could. Do you want to try? Shall we try now? Or should we do it in one step? One step. Anybody else? One step. Yeah. All right. Let's do it in one step. In the lab, you have B already, right? B is 1, 1. You have A, 1. Was it minus 1/3? Yeah. Y equals to filter B, A, then what? 1, 0. I mean, however many you want. Finish. 2 steps. 3 equations. Let's try, guys. B, A. Okay? Y equals to filter B, comma A, 1. That means the impulse. All the rest are 0. However many you want. And answer is 1. 1.3. So that's it. The sequence is there. All right. And in fact, the 0 here doesn't die. Huh? All right. So let's record this number first. Equals to 1, 1.33, 0.44, 0.1481, 0.0494, and so on. So in the exam, if I ask you find values of Hn, then all you do is this filter BA, an impulse, and you get the number. And you list it for me in 2, 3 times more place. So this is one way. How many other ways you can do this? This is the brute force way. B. How about getting the closed form solution? This is non-trivial already. What can you do, guys? So if I ask you for a sequence of number, it's trivial. Yes, we do Z transform and inverse Z transform. So H of Z, we had what? Let's pull out H of Z again. Z plus 1, Z minus 1/3. Z plus 1, Z minus 1/3. So Hn equals to inverse Z transform Hz. Again, one step if you have MATLAB. Okay, let's try. So symbolic Z. So Z is a symbol. Hz is equals to Z plus 1 divided by Z minus 1/3. Actually, it doesn't matter whether I'm doing it in what do you call that? In positive powers of Z or negative powers of Z. Hn equals to inverse Z transform Hz. Answer is this. Okay. And I'm going to copy the answer for you now. And then it says h of n is equals to 4 to the power of 1/3 n minus 3 delta n. Okay, so this is the answer using the Z transform of MATLAB. Now, if you're in the exams, of course, you're like, oh, how are we going to do this, guys? So, what should I do if we're in the exams? So, you should take this equation, the top one, and you do by partial fraction. Hz is equals to what? A over Z minus 1/3, right? Plus, oh, what should I do? Hmm. Anybody? Okay, I'm just going to cheat as usual. RPK, residual Z, 1, 1, 1 minus 1/3. Can you see? I know that it will reduce to, I mean, I hate doing partial fractions, guys. Answer is 4, 1 minus P, 1/3, Z minus 1 plus minus 3. Okay. Anyone believe that this equation is equals to this equation? Let's say I don't believe, right? So I'm going to try. 4 over, so I will multiply top and bottom by Z, Z minus 1/3. So nothing is changing here. Minus 3, I have to multiply top and bottom by Z minus 1/3. So nothing is changing here. So now I can collapse these two. 4Z minus 3Z plus 1/3 divided by Z minus 1/3. 4 minus 3 is Z. Z plus 1/3 divided by Z minus 1. Did I make a mistake again? Oh, of course I made a mistake. 3 times minus 1/3 is plus 1. So on top is Z plus 1, Z minus 1/3. So from this guy to the partial fraction expansion, you can use residual Z. Okay? Don't use residual. Use residual Z. That's what I did. So I will show you the trick. If you're next, you've got MATLAB, right? Is RPK equals to residual Z. And this is B, and this is A. And B and A are in negative ascending power of Z minus 1. Okay? So therefore, that's why don't switch between S and Z. Don't. Right? S likes positive powers of Z. Positive S plane, the Laplace plane like positive powers of S. In the Z domain, we always play with the negative powers of Z. Okay? That's why B's and A's are in negative ascending powers of Z. Now, then we do RPK. RPK, yeah, with B and A and R and P and K. What is R, P, and K? Right, help residual Z. Now, am I asking you to study MATLAB? No, no. MATLAB is simply a calculator. That's it, a symbolic calculator for us, allowing us to call functions such as, residual and uh, Z plane and things like that. You have to still be able to do it by hand if necessary. All right, let's see. First, residual of Z B's and Z's are in representing the H of Z. RPKs are vectors, and what the vectors comes out is this. B over A is equals to R1, the first element of R, big R, divided by 1 minus the first element of P times Z minus 1. So we are always living in the Z minus 1 negative powers of Z. Plus, then the next one divided by 1 minus P n divided times, and so on. Now, the k's are interesting. K1, the second k is K2 times Z minus 1. So therefore, you always have to keep on playing with this until you can, get it right. Okay? And I mean, and sometimes, just for sanity check, I always, even though I get the answer, I will, I will open it up again to make sure that I get the original expression. All right. So now that I have gotten the original expression, let's now erase this. So now we believe that the partial fraction is correct. So what do we do for the partial fraction? Inverse Z transform. Minus 3 becomes, guys, the the minus 3. Inverse Z transform of minus 3 becomes Mugu says that don't have residual Z. Impossible, guys. You help residual Z, and maybe I guess you didn't install some libraries. Okay, Mungo try. So yes, he's right. Minus 3 delta n. What about this here? Becomes 4 what? 1/3 n un. Therefore, this becomes hn. Clear? And then you can of course then work it out for different ends, and you will get this sequence as well. The filter actually is doing our brute force, you know, really, really running this guy, really running this guy, pop, 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 generating access, pushing it into memories, getting the output summing. That's filter, okay? But if you are doing closed form, you don't need, right? You, you just this, and of course you substitute different ends, you'll get answer. Okay, are we almost done? Ah, okay. Another few minutes and we're done. All right, guys. Just mm, let's let's sketch a cosine 0.25 pi n. N equals to 0 to 10. What x equals to a less is 1 times cosine omega is 0.25 times pi n. Plot stem n x. What do I get? Close or The stupid line doesn't come out. How should I do it? There's a bug in MATLAB, okay, guys? All these guys should be aligned, yeah? Oh, I remember solving this problem before. Hmm. How to thicken the line? But you guys can see the line. All right, not going to use the stem. I'm going to use the plot. Now I'm going to use the hole. And now I'm going to use the stem. And then now I'm going to use the red. And what do I see, guys? All right, now you can see the... Okay, can you see the cosine wave? It starts from n equals to 0. And then as n goes down, it comes here. 2 steps later. Why 2 steps, guys? Why 2 steps? Why does it take 2 steps to reach 0, 3, 4, 5, 6, 7? At 8 step, it reach here again. 1. Why, guys? Can someone tell me? So, so the question is, x of, oops, when does x of n plus big N equals to x of small n? What is big N? Anybody? No, no, I'm asking what is big N. Oh, okay, okay. The rest of the guys, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 guys with the camera off. I've spoken for 1 hour now. Could I ask the rest of the guys to turn on your camera, please? You know, in MBS, right, they make everybody turn on the camera. Please? Oh, guys. Yeah, this is like, mm, my goodness. Okay, big N is 8. Why does it 8? Because you can see that it takes 8 times. But where did this 8 come from, guys? Where did this 8 come from? How would you know? Because A cosine pi over 4 small n plus big N, when is it equals to, when is this guy pi over 4n plus 2 pi k? So the interesting thing is that is the pi over 4 big N must be equals to 2 pi k. So pi disappears, then the what? Capital N stays 8k. Then I'm interested in what is the k, guys? The k is how many times I'm rotating. I'm only interested in one rotation. So once I substitute n equals to big 8, I will have rotated by 2 pi. Clear? Okay, everybody? So this is the first interpretation. What is the second interpretation, guys? Every step, right? I am moving along time. How much? How fast? How fast? Yeah, radian. Am I moving? What is the angular frequency? In other words, anybody? Come on, staring at your face. What is my angular frequency of this cosine? Pi 4. Can you see here? And what is the unit? Its name is called angular frequency. And its unit is called unit, guys. I'm running. How fast per time, per step? I'm moving by how much radian per step. So it's radian per sample. Very good. So, so guys, what is the range of radian per sample that I can really use. What is the frequency range? If this is radian per sample, right? So you have seen 0. You have seen pi over 4. Of course, you can say pi over 2. What is the rightmost, guys, that I can use? Infinity? Yes? No? Maybe? Come on, guys. How far can I stretch before it becomes useless? Minus 2 pi to pi. Ah, not quite. Why not quite, guys? Pi, 2 pi, minus pi, minus 2 pi. Now, what is the range, guys? It's not minus 2 pi to 2 pi. Give me another different answer. Come on. 0 to 2 pi. Excellent. That's one answer. 0 to 2 pi is a valid choice. Another choice. Minus pi to pi. Very good. Why is it? Why is this guy? How is this? So this is overlapping. No question. It means that this guy are the same. Why? Why is this guy? Okay, yeah. If I'm here, right? If I am at 1.9 pi, let me draw 1.9 pi here. If I at 1.9 pi, where is my equivalent in the range of 0 to minus pi? Where do you think it is, guys? Come on. 1 mark for DSP for your lab. No lah, 1.9 pi, 1.9 pi. 0.9 pi, no. Okay, let's try, guys. Let's try. 0 is equivalent to who? No. 0 is equivalent to 2 pi. Why? Okay. Now look at my pen. My pen is here. And can you all see? Yes, see my pen? And if I move 0 radian per sample, my pen stays still, right? Yes? Everybody happy? Now if I move 2 pi radian per sample, I'm moving one round, right? Pop, 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 pop. One complete round. 2 pi, yes? In your eyes, did my pen move? No. My pen in one step moved by 2 pi. Pop. But your eyes only can see at time 0 and time 1. As I'm moving by 2 pi during time 0 to 1, which is continuous time, your eyes can't see it. That is why 0 radian per sample is equivalent to 2 pi radian per sample. So now that it's obvious, who is 1.9 pi? Come on, guys. Where is he? He's equivalent to minus 0.1 pi. Why? Where is 1.9 pi, guys? If this one complete round is 2 pi, anti-clockwise, right? Positive angle. Who is minus 0.1 pi? He's moving a little bit down by 0.1 pi. But look, 1.9 pi is rotating anti-clockwise by a huge round and reaching at the same point as minus 0.1 pi. Clear? Everybody? Yes? No? Maybe? Am I boring y'all? There's only 13 of you. I can talk about this. Yes? Clear? Very good. So now, in the digital world, our little omega can be only 0 to 2 pi. And in fact, right, we are lazy. We only plot 0 to pi sometimes. Because actually you'll realize that from pi to 2 pi, it's going to be some symmetry, and then we know the symmetry and we don't care. All right. Okay, where's my question? So I'm going to fire a cosine 0.25 pi into a system, and out comes the output. Can I do this by brute force? Okay, let's show you. Brute force. I already got my x. Yeah, I've got my x, right? Now, y? What do you think I'm going to write, guys? Come on, guys. I have MATLAB sitting in front of me. What will I write? Yeah, cool. Thank you, Ikang. Filter b comma a x. That's the output. So now close all. Now I want to do plot, plot, plot n x. Blue dash line. I have my input, and now I also hold on plot and y rate. And now the question is, what happened, guys? I see my input, and now you see my output. What happened to my output? It has become bigger and phase shifted. Very good. Amplified and phase shifted. And then, of course, if I ask you to measure the gain, then it's a horrible graph that I'm giving you, because it's the cosine wave is so sampled that it doesn't really look like cosine wave. I mean, you can still guess, and the gain is from 1 becomes 2, and it's phase shifted. And if I ask you for the frequency, the phase shift and things like that, it's hopeless. So, guys, at this point in time, please do this. Frequency response. H of z is equals to, what's my equation again? 1 plus z minus 1. 1, what's my equation? 1 plus z minus 1, 1 minus z. 1 minus 1 third z minus 1. Agree? Happy, everybody? Of course, I don't like negative powers of z. I have no idea how to do this. So this is the same. Nothing happened. H E j omega is the frequency response. Is equals to h of z equals to what, guys? This is the thing that you have to memorize. What would I put in this little box here? E j omega. Very good. E j omega. So therefore, now all my z becomes e j omega plus 1 divided by e j omega minus 1 third. So now I'm interested in what? Interested in where? Omega equals to? What was my question? In the previous one, 0.25 pi. Correct? And now what do I do? Therefore, h of e j 0.25 pi is equals to e j 0.25 pi plus 1 e j 0.25 pi minus 1 third. And the answer is, come on, guys, h j omega is equals to exponent j times 0.25 times pi plus 1, that's the numerator, divided by exponent of j times 0.25 times pi minus 1 third. Answer. Huh? Oh, j. All right. That's some lousy rectangular number. 1.779 minus 1.4738 j. What must I convert to, guys? What form? So I want to do polar form. So it's absolute of HJW. Answer is 2.331. And the angle is angle minus 0.69. Now, now, how do you think I'm going to convince myself? How do you think I'm going to convince myself that my red line is correct, guys? I will construct a green line based on these parameters. Okay, so now is y estimate is equals to 2.3102 times cosine 0.25 times pi dot times n minus minus 0.6918 y estimate. Oops, I got y estimate. And now I'm going to plot onto my green. Now I use my x, and now I call it y estimate. And voila! I got it wrong. No, I didn't. Okay. All right, guys. Look at the magic. After the third sample, the fourth sample, the green line and the red line overlaps completely. Can you see? Yes? Happy? And in the beginning, they were not overlapping. Why? Because in the beginning, the red line, the memories were all zero, right, guys? Yn minus 1 was 0, xn minus 1 was 0. That's why this is the real thing that is going to happen. The green line is a real cosine, right? It's an infinite cosine showing you that this is the response I'm getting. So this is the transient response, okay? And after here, the fifth sample is the steady state response. So if I'm interested in the steady state response gain, the answer is 2.31. You will amplify my signal from 1 to 2.31. You will phase delay my signal by 0.69 radian. Clear, guys? Happy? Mm. Okay. So so now you know, right? So this is the magic of HZ. In HZ, I am simply substituting my Z as EJ omega. And in fact, I'm not even substituting the entire omega. I'm only interested in one point at 0.25 pi. So now if I'm going to ask you, plot for me all the all the omegas from 0 to 2 pi, then all you are doing is writing a for loop. That's all. Okay? So in fact, I will show you my answer. What's my equation? 1, 1. Yeah, so this is B and A, right, guys? Okay, run. All right, so this is the from 0 to pi. 0.25 pi, somewhere here. 0.25 pi. Come on. 0.25 pi, my gain is 2.2. Was it? Answer 2.3. Yeah, about. Let's expand this. 0.25 pi is where? 0.25 pi, maybe here. Yeah, somewhere here. Okay. My gain is about 2.31. Correct. So this is plotting from 0 to pi, plotting the different gain. So it's a for loop that is running. The other way I can show you is this. This is the 0. 0 is sitting at -1. Pole is sitting at 1/3. I draw a circle. And then I also, this is my Z plane. And now I'm going to plot for you my magnitude gain. And then now you can see that the magnitude gain is going from 0 to 2 pi. And you also realize that, hey, once I plot 0 to pi, I'm not interested to plot 0 to minus pi because they are symmetrical. Okay? So that's why nobody cares about the other minus pi to pi, 0 to minus pi. Now, then you'll be thinking, what is the world, how is this curve, red curve, related to this curve? Anybody? I told you that they are the same curve, but yet they look so different. So I must be orientating it wrongly for you. I must be orientating it this way for you because this is, I must be orientating it this way. Can you see? Whoa. Yeah. Then you can see that actually. I also have no idea why is there distortion here, but never mind. But they are the same curve. All right. What about 0.25 pi? I should. Okay. This is 0.05 pi. I'm going to plot for you 0.25 pi. Okay. Where's my 0.25 pi? Here. 0.25 pi. I'm going to run 100 samples per. Throw away all this. There. The green is the input. The blue is the output. The gain is 2.31. Phase is minus 0.69. So again, in the front few samples, they were wrong, but after a while, they all converge. So this looks good. Now, this looks very poor because every sample I'm moving by 0.25 pi. So if I use a slower frequency like 0.05 pi, you see a very smooth input. Nice. You see a very smooth input. The green is the input. The blue is the output. The red is the infinite cosine that is going to be multiplied by 2.96. So you see that the blue, the initial front part, will not correctly outputted. It is because the filter is relaxed initially. So until the buffer of the memory of the filter fills up, then it becomes constant. So this is the transient condition due to zero initial condition. All right, I think I'm almost done. Anybody else? Any questions? With this, right, you can do the lab for sure. Okay? I mean, if you're writing the lab like me, you'll be done in 30 minutes. Actually, honestly, if you have done all the labs, then you'll be realizing that all you're doing is go there and change the equation, you know. So change the B's and the A's. I change the different one, and I just run, and now I get different values, right? Whatever values I want. That's it. So this is the impulse response. Pop, 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 pop. All right. Now I'm going to ask you this. This is the filter that I'm playing with. 110 for B, 1 minus 1/3 minus 2/3. Something is wrong, once you see the output. First, the impulse response. First, the pole and zero. What's wrong with this pole and zero, guys? What's wrong? Anybody? Okay, Julius asked whether it's x square bracket n or x curly bracket. For me, I don't care. Normally, you want to write square bracket so that you remember that n is discrete time, but it doesn't matter. Nobody cares. On the unit circle, I don't understand. Oh, yeah, yeah, yeah. The pole is on the unit circle. Therefore, it is partially stable. Partially, yeah. It doesn't blows up, okay? Partially stable. Why partially stable? Let's look. Let's look at the impulse response first. That's my impulse response, guys. Here's my impulse response. Pa, up, down, up, down, up, down, up, down, down. But it stays at 1.2. It means that when you send an impulse, the output doesn't die. When the output doesn't die for impulse response, then the answer is that it is not stable already, right? And so we see it two ways. We see that the pole is on the unit circle, and we see that the impulse response does not die. Can? So this is. Mm. And now when I try to use the frequency response Hz equals Hej omega, it doesn't agree, huh? Because already the theory tell us if the filter is not stable, then Hej omega is wrong. Okay, we can't really use it, but it's still very close. All right, unstable. All right, let's try on some unstable guys. I mean, you're still plotting something, but you're thinking, hey, does it work or not? Let's try. Here, the pole is outside, okay, 1.05, outside the unit circle. So for sure, this is unstable. Now look at the impulse response. Pa! So now I plot. If I plot some more, it's going to blow up, right? And now the input, I send this, the blue one, wow, it's blowing up now. Okay, for sure it's unstable. Can? But frequency response and all this you still can calculate. So don't believe the things when it is unstable. Then Hej omega don't make sense at all. Can? It's uh just math. But it's wrong. Okay, I'm gonna plot for you longer impulse response now so that you can see that it's going to be unstable. So I now have 130 samples. So honestly, guys, if you have written your code, you're just going to the lab and changing a few numbers. See? Where's my impulse response? Ah, yeah, there. Beautiful, isn't it? Blowing up. My impulse response. Okay? Blowing up. I mean, all you the writing is just filter BOA, right? See? That's it. Filter BAX impulse. And I'm changing the length of my impulse. Now I give you 1,100 samples. There. Wow. Wow. After 1,000 sample, it's going to 10 to the power of 22. Okay? So, so things like that. All right. Now, I'm going to, yeah, show you a nice one. I haven't show you complex holes, huh? Pa. Okay. What does this look like to you? Stable or not stable? Stable. The poles are on the unit circle. Okay. Figure 2. Impulse response. Pa. 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 Dice. Looks good. I'm sending cosine 0.05 pi. Pa. Boom. 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 The green is the input. The the who the red the red crosses are the infinite response, and the blue is a simulated filter BA. Initially it's like terrible, right? Pop, 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 pop. But after about 40 samples or 50 samples, it's exactly following the rate. Why? Again, it's memory, right? The memory is not being filled up yet. It's not like it's still, it's still trying to learn how to behave properly, and it's behaving properly after, then it's actually proportional to when this guy is dying to or close to zero. So about 80 samples later, yeah, it's almost perfect. Can? So you always look at the impulse response, and then you can simulate and you know what's happening. All right, last question, guys. Look at the frequency response. So again, it's two when it's about no omega equals to zero, and it becomes higher and higher. At zero point 0.3, wow, it becomes like 18 times and then it dies again. So it's about 0.32 pi. Okay, let's change. I'm going to I'm going to change my code 0.32 pi. Where's my input? Here. My omega. Where's my omega? Okay, here. 0.32. And I told you that the gain is about 18, right? Let's run. So at 0.32 pi, the gain is about 18. Ah, it's so hopeless to see, but you can see the green is 1 and it's about, yes, 18 times. Can? And it's hopeless because the higher the frequency, what? It's very hard to observe the cosine very well. Now let's observe 0 radian. At 0 radian, my gain is 2.24. So 0 radian, run 2.24. So the red line, see, 2.24 exactly. Can you see? And the blue, is oscillating, and after about 80 samples, become flat. So this is the step response. This front part is a transient response, and after 18 samples. But I'll show you now using 200 samples, and it's nicer to see. See, nice, huh? After about 100 samples, it's going to flat. The red is the the steady state response. The blue is the transient plus the steady state response, the general response. The green is the input. Okay, Ken, I'm done. I've taught you almost everything of this whole diagram, right, guys? See? So in 2 hours, we have went from the difference equation to the block diagram to the Z domain, the system transfer function, to the poles and zero. We show you how to calculate the Hn using brute force as well as inverse Z transform, and we used Hej omega. All done in 1 hour and 40 minutes. All right. Now, with that, can you all tell me how was it for you?